Okay, great. Thank you very much for the kind introduction, and thanks to all of you guys for coming to listen to me talk today. So, as you've probably got by now, I'm here to talk about prime numbers. And in particular, prime numbers seem to have this space in the public consciousness of being the ultimate symbol of obscure mathematical geekery. And what I'd like to try and persuade you today is that actually prime numbers are some of the most simple and fundamental objects you can possibly imagine in the whole universe. But more than just them being important in this way, they're also completely mysterious and fascinating because they're very poorly understood and difficult, despite at the same time as being so simple. So the basic question that I'd like to talk about is, why on earth should you care about prime numbers? That maybe you've heard about prime numbers, but why on earth should a mathematician or someone in the general public have even heard of prime numbers, let alone spend any time thinking about them? And if you're of my millennial generation, then maybe you're told that you have a very short attention span. So the 1-minute tagline is that primes are these very fundamental, basic building blocks of the universe, but despite, on the one hand, being the most natural, simple objects you can possibly imagine, they're also somehow unbelievably complicated, and we really don't understand them at all, even though mathematicians and some of the smartest mathematicians in the history of mathematics have been trying to understand them for thousands and thousands of years. So if all you wanted was a 1-minute summary, that's fine. You can wander out now. If you'd like to hear a tiny little bit more, this is roughly how I envisage trying to persuade you that primes are both important, but also beautiful in their own right. So first, I'd like to explain why the primes are important, particularly to mathematicians, as fundamental building blocks of nature and the universe. And then I'd like to illustrate this point about primes being both important on the one hand, but exceptionally complicated and poorly understood on the other hand, through two different examples. So my first example is going to be a problem coming out in the real world. Both of the examples are slightly artificial, but they're here to illustrate the point. So it's going to be a real-world problem that both sees the fact that primes are these fundamental building blocks, but are somehow at the same time very poorly understood. And then secondly, I'd like to give an example in pure mathematics, which is completely on the other end of the spectrum, where again, primes as fundamental building blocks play a super important role, but they quite quickly lead to questions that we've been thinking about for hundreds and hundreds of years, and we don't understand at all. Now, at this point, you might be slightly depressed, because maybe if I've been successful in convincing you, you'll accept that there are these important objects, but you might also feel that all these super smart people, these old white guys from thousands of years ago who've spent their time thinking about it, and if they can't do anything, and we've been trying for hundreds of years to do anything, how on earth can we possibly say anything at all? So I'd then like to try and end on a slightly positive note, that despite there are being all these very basic questions about prime numbers that we really don't understand at all, we have nonetheless been able to make some progress on prime numbers, and we are able to say something new about it, and progress is really happening now. Okay, so let's move on, and the first stage is primes as building blocks. So this is really why I think of primes as important objects, because they're somehow very much the building blocks for mathematicians. But before we get ahead of ourselves, let's remind ourselves what a prime number is. So if you look on a textbook, or maybe if you go on Wikipedia, you'll find the following, or something like this, is a rather dry definition of what prime numbers are. So a prime number is a whole number which is bigger than 1, and it can't be written as two smaller whole numbers, multiplied together. So 15 is not a prime number, because 15 is 3 times 5, which is writing it as two smaller numbers, but 7 is a prime number because you can't write 7 as two smaller whole numbers multiplied together. But a fairly natural question, if you see this definition for the first time is, so what? Okay, fine, you can call a prime number this, but this doesn't mean anything. It seems completely artificial. We've got this somewhat arbitrary point that we're saying that prime number has to be bigger than 1. Why isn't 1 a prime number? And why on earth should you care about writing numbers as two smaller whole numbers? And this is a pretty reasonable question, I think. But it is the case that primes are important, and that's because this definition is actually precisely the right definition and is incredibly useful for mathematicians. So what do I mean by useful? Well, scientists, and I think in my experience mathematicians in particular, are lazy. Okay? We often spend our time thinking about very complicated, big systems of interacting things, and it's really difficult to think about these things. It really hurts your head to think about them. So rather than often directly attacking this big, complicated problem, we found this trick of just breaking the problem and viewing it as lots of smaller problems all multiplied together. And if we can understand the little elements that make up the big problem, then maybe we can understand something about the big problem. And this isn't a principle in mathematics only. It's a principle that cuts all the way across science and wider. If you're studying for your GCSEs, then I remember when I was studying for my GCSEs, there was GCSE bite size, which was about breaking up your revision into smaller blocks. So for example, if you're a chemist, then maybe you want to study large chemical compounds, very complicated objects that have lots and lots of things. But we know that chemicals are made up of lots of atoms joined together. And if you know what atoms make up a chemical and how they're joined together, you can understand some things, not necessarily everything, about the big complicated chemical. Similarly, if you're a geneticist, maybe you're interested in some genetic disease, and you can begin to understand something about the genetic disease by looking at the base pairs and sequencing parts of the genome to understand different alleles as part of the gene, which determine the genetic phenotypes. And so both of these are big, complicated problems that you can understand, at least in part, by looking at these small constituent parts. And there's just a relatively small number of choices of possible atomic elements. This is the famous periodic table. Similarly, there's only a very small number of possible choices of base pairs, and so relatively few relevant alleles for your genes. Okay, so it's all very well talking in this abstract language about nice principles of breaking things into smaller blocks. How would this possibly work in maths? Well, I'm a number theorist, and so as a number theorist, I want to investigate and study properties of the whole numbers. And okay, you might think that the whole numbers are very simple, but to me at least, the whole numbers are very complicated. Questions that I might be interested in is if you write down some equation, does this have a solution in the whole numbers or not? And in fact, this seems to be a very, very difficult question, which we know in general doesn't have a computable answer even. It's undecidable. But in slightly simpler cases, we might hope to understand something about questions involving the whole numbers if we can break that question down into simpler building blocks. But whole numbers come with various very natural operations that you can do to them. In fact, there's two natural operations. You can add whole numbers together, and if you add two whole numbers together, you get another whole number. Or you can multiply whole numbers together to get another whole number. Subtraction and division are essentially the inverse of addition and multiplication. And so you can study the whole numbers from the point of view of addition, or the whole numbers from the point of view of multiplication. And from the point of view of addition, all the whole numbers are generated just by the number 1. You get any whole number by just keep on adding 1 to itself. And this means that certain questions about whole numbers, particularly if they're of an additive flavor, very quickly become exceptionally trivial because they just boil down to a question about the number 1. So what are sort of gaps between whole numbers? Well, all gaps between whole numbers are just 1. So this is a weak example of this concept of breaking complicated things down into simpler things that works exceptionally effectively. Basically, because the primes are just generated by this one number 1 from, not the primes, the whole numbers are generated by just this one number 1. But from the point of view of multiplication, things suddenly become much, much more complicated. So whole numbers are generated by prime numbers. Every whole number can be broken down into prime numbers, but then they can't be broken down any further. And this means that if you have a problem about the whole numbers that involves multiplication in some way, then you might hope to break it down into a simpler question about prime numbers. But there's then various difficulties because you need to understand the simpler problem about prime numbers, and so you need to understand something about primes. So my life would be a lot easier if number theorists had our own periodic table where it had a list of every prime number, and then maybe you would have some problem involving multiplication, and we could reduce this to a problem about prime numbers, and then we could go through each prime in the periodic table and solve the problem for each prime, and then we'd be done. However, it's a famous result from the ancient Greeks that there's infinitely many prime numbers, and so this isn't a very good approach to doing things since we'd have an infinite-sized periodic table, and so we naturally need a more theoretical understanding of how things can work so we can deal with all primes at the same time. But this concept of primes being the building blocks of numbers, and from the point of view of multiplication, every number being able to be broken down into primes, is an absolutely fundamental one in mathematics. It's so fundamental that we give it the funny title, the fundamental theorem of arithmetic. So this essentially goes back to the ancient Greeks, and this says that every whole number, which is bigger than 1, can be written down uniquely, apart from the order in which you multiply the numbers, as a product of primes. So 15 can be broken down as 3 times 5, and there's no other prime numbers that can possibly come up. You can't have another way of writing 15 that would be 2 times 7. It always has to involve 1 3 and 1 5 and nothing else. And this is also why we say that 1 is not a prime number, because if 1 was a prime number, you could write 15 as 3 times 5, or 3 times 5 times 1, or 3 times 5 times 1 times 1, and so on. And there'd be lots and lots of different ways of doing it, which would then mean that 1 would somehow be this annoying exception, and every result about prime numbers would say, let P be a prime that's not 1, because 1's this funny prime that keeps on messing everything else up. So in this way, you can think of, if you want to visualize things, you can think of primes as being the atoms that make up the chemicals of integers with respect to multiplication. So 135 is 5 times 3 times 3 times 3, and so here's my visual representation of 5 times 3 times 3 times 3. And if you somehow understand questions about 3 and 5 very well, then you might hope to understand questions about 135 very well. And I at least claim that somehow questions about 3 and 5, by virtue of being these atoms that can't be broken down anymore, are fundamentally simpler than questions about these more complicated numbers that have lots of different factors. And this is really the reason that I think primes are important, that these are these fundamental building blocks of whole numbers. So Kronecker was somewhat unusual for a mathematician in the sense that philosophically he didn't really believe that maths was out there and mathematicians just discovered truths of the universe. He felt that lots of the work of mathematicians was somehow artificial constructs of man. But even to Kronecker, he said, God made the whole numbers, everything else is the work of man. So even to Kronecker, he decided that the whole numbers are somehow so fundamental to the universe that they were made by God. And similarly, if I try to imagine an alternative universe, I could potentially go a bit crazy and think of something where gravity didn't work in the same way, we had different fundamental forces, maybe life didn't exist. But I can't possibly imagine a world where there isn't some concept of the whole numbers, of just counting 1, 2, 3, 4, 5, and so on. And if I can't imagine a world without whole numbers, then I certainly can't imagine a world without the building blocks of whole numbers, which are the prime numbers. And so it's this fact that the prime numbers are these really fundamental building blocks of the whole numbers, which are maybe the most natural objects in the entire universe, that is really why I think of primes as important. But that's not necessarily why I find primes interesting. And the real reason that I find primes so fascinating is this contrast between, on the one hand, you having these exceptionally simple numbers, just the whole numbers, almost the simplest thing you can possibly imagine as an abstract concept. And very naturally from them, multiplying numbers together, you break them down to their building blocks, and then you ask some exceptionally elementary question about prime numbers, and we don't know how to solve it. So it's the fact that on the one hand, primes seem to be exceptionally simple, but on the other hand, exceptionally complicated, that is really what fascinates me about primes. So Gonzaga says it much better than I possibly can. So this is a quote from him. Despite their simple definition and role as the building blocks of the natural numbers, the prime numbers grow like weeds amongst the natural numbers, seeming to obey no other law than that of chance, and nobody can predict where the next one will sprout. And somehow this very much captures the fact that even though primes are completely rigorously pinned down, you can ask your computer, is this large number a prime or not, and it will say yes or no. To all extents and purposes, from the point of view of mathematicians, they look as if they just appear randomly, and we have no understanding at all. So just to give one example of this, you might have heard of the Riemann hypothesis. It's dubbed sometimes the most important problem in mathematics. And if you had a good answer to how many primes are there which are less than some large number x, then essentially you would have solved the Riemann hypothesis. And this would make someone like me exceptionally happy. We'd have a fantastic understanding of prime numbers. If you couldn't care less about making me happy, then maybe you'd be happy because the Clay Maths Institute, based here in Oxford, have offered $1 million for the solution, and so you'd be a little bit richer. But this is one of the most basic questions you can possibly ask about how often do prime numbers come, and the answer is, well, we don't know, we haven't known for hundreds of years, and we're so stuck on this that we view it as one of the most important problems in the whole of mathematics. Okay, so that's given a slight feel of why primes are important, because they're these fundamental building blocks of the whole numbers, which are the most natural objects, in my mind, in the entire world, and also why they're fascinating, because even though they have this very fundamental definition, they're really so poorly understood, and they look as if they could just be coming at random. And I'd like to explain these two properties through two examples. And so the first one is a real-world example. So maybe some of you at the back are a little bit bored and you're playing on your phone. And if you're playing on your phone, maybe you decide that a good thing to do would be to make the world's richest man a little bit richer by buying something on Amazon. So again, I'm a number theorist, so the sort of things that I find exciting to buy on Amazon are books about number theory. Maybe you find something else exciting. But certainly if you were going to buy something on Amazon, it would be pretty important that your credit card details could remain secure. So depending on your politics, you can view this nefarious figure as some teenage anarchist or some shady government organization. But one downside of the internet is that whenever you send a message to someone else over the internet, in principle, it's very easy for someone else to eavesdrop and to hear what you're saying. And so to get around this, you need to have some code so that you can communicate with someone else, and even if someone can literally hear what you're saying over computer cables, they can't work out what that means. It's as if you're talking in a secret code language. And so the way that this is done is by turning your secret information that you'd like to pass along into some number, and then doing some mathematical operations to encrypt the number in a way that it's very difficult for someone who knows nothing secret at all to decrypt, but someone on the other side can decrypt without too much difficulty. And so there's various clever ideas as to how to do this, but the key point is that all of these commonly used crypto systems for this sort of setup involve multiplying numbers together and doing things that look like multiplication. And so this is a problem that's involving whole numbers being multiplied together. And so because prime numbers are the building blocks of whole numbers, you might naturally think that you can try and understand the situation a bit better if you look at it from the point of view of prime numbers. Either if you want to yourself be the hacker who's hacking someone else's details, or if you want to be the person who's reasonably confident that someone else isn't going to be able to hack your details. So there's a few different ways of encrypting things, but one of the common ways, roughly, you can analyze from the point of view of prime numbers, and the whole question boils down to, is it easy to factor some large number into its prime numbers? So we've seen that every number can be written uniquely as a product of prime numbers, but that doesn't mean it's necessarily easy to do this. If I give you some large number, can you write it as its prime factors? So for example, you could take the number 449,623. Can you write it as prime factors? OK, I can see that everyone can tell that this is obviously 521 times 863. And this isn't too difficult, at least for your computer, because it can find these factors very quickly. However, when the numbers start getting larger, we believe that this very quickly becomes very difficult, and this means that it's very difficult to hack any internet communications. So for example, you could take this slightly larger number, which I'm not going to read out for you, and those of you at the back who are bored and buying things on Amazon, well, you can go on a bit more of a spending spree because you get $75,000 if you know how to factor this number. And one thing I'd like to point out is, although this number is certainly quite a lot larger than the other number, it has maybe 100 times as many digits, but your laptop can do this factorization in less than 100th of a second very easily, whereas it would take 100 supercomputers more than 1 billion years to factor this number, as far as we know. So it really becomes much, much harder to factor numbers as you get to bigger and bigger numbers. We don't have any theoretical proof of this, but this is at least what we believe, and so we therefore believe that when you buy things on Amazon, your credit card details won't get hacked. But the example is less about the precise cryptographic protocol, but more, this is a very real-world example that boiled down to a problem about multiplying numbers together, and because it involved multiplication of whole numbers, it could be understood via prime numbers, and prime numbers allowed you to get a feeling of whether this was easy or difficult. But you can actually analyze this a little bit more if you think a bit more from the point of view of prime numbers. So it's a fact, and it's not a super complicated fact, that you can factor a number easily if it has factors, prime factors, say call one of the prime factors p, where p minus 1 itself only has small prime factors. So this seems like a fairly odd thing. You take a number, you take one of its factors, you take one away, and then you factor that. And if all of those factors are very small, then there's a quick way of factoring the original number. So this is another example of prime numbers being used to say something about the original problem. So for example, you could take the prime 2 times 3 times 4 times up to 320, then add 1. That is in fact a prime number. And this, when you take 1 away from it, it only has prime factors which are smaller than 320. And then if you gave me some large number, which is this prime times some other big thing, but you didn't tell me that it was actually a multiple of that prime, but you did tell me that it has a prime factor p, where p minus 1 only has small prime factors, then it'd be very, very quick for me to factor it, even though this number is much larger than the $75,000 number that I put up on the previous slide. And so this is another example of primes understanding the situation, But then the sorts of questions that I'm really interested in are how many primes are there with certain properties? And so a natural question you might have based on this is, how often is it that p minus 1 only has small prime factors? If this happened virtually all the time, then you should be pretty worried about buying things on Amazon. Now, fortunately, we know a little bit about this problem, although not a huge amount about this problem, and we know that it's not very common for p minus 1 to only have lots and lots of small prime factors, and therefore you don't need to worry too much about your internet purchases. But despite this, it has been suggested by some people who work on this that because it's really bad if p minus 1 has lots of small prime factors, you should do the opposite thing and have it as having as few small prime factors as possible. Now, all primes bigger than 2 are odd, so p minus 1 is always going to be an even number. So maybe the furthest thing you could possibly have away from p minus 1 only having lots of small prime factors would be if p minus 1 was 2 times some other large prime. This way of trying to hack your credit card details will completely fail. And you could be a little bit secure that this is a safe prime to use. And so these are indeed called safe primes. And actually, it is an option in some of the very common internet protocols to use safe primes, even if it's not the typical default option. But then there's another question. How many of these safe primes are there? Imagine you did want to only use a prime p where p minus 1 over 2 was a prime number. Well, if there aren't any of these primes, then you're not going to be able to communicate with Amazon at all. Your laptop's just going to sit there thinking and thinking, looking to try and find one of these things that doesn't exist, which means you certainly won't be able to buy your number 3 textbook or whatever it is that you were wanting to buy in the first place. However, it'd almost be even worse if there were a few of them, but only a small number. Imagine there's only 10 of them out there of the right sort of size that your computer's looking for. Then maybe your computer will find it, it'll communicate, but maybe the hacker can also find each of these 10 numbers, can try them each one by one, and then can hack your details really, really easily. So a natural question is, well, what do we know about these safe primes where p minus 1 over 2 is prime? And we believe there should be lots and lots of these, but this is an example of a famous unsolved problem on prime numbers, which has been open for hundreds of years. So you'll become very famous if anyone solves this during the process of my talk. Just are there infinitely many primes such that p minus 1 over 2 is itself a prime number? This is very much an open problem, and we really don't know how to solve it at all. But this is a question that naturally arises if you're using these cryptographic schemes to buy something on Amazon. So that's just basically what I said before. It's one of the most notorious problems. OK, so that's my example of a real-world situation, just buying something on Amazon that very quickly gets related to encryption and multiplying numbers together. Because it involves whole numbers multiplied together, you can break it down into a problem about primes. You can start to understand the situation by primes, but quite quickly you start getting into questions about how many primes are there with this sort of property. And unfortunately, you quite quickly run into famous 100-year-old problems that people don't know how to solve. OK, so I'd now like to change gears completely and go to the complete opposite end of the spectrum and give an example as to why a pure mathematician might care about prime numbers. Say you're a number theorist, but you don't work on prime numbers per se. And so my example is going to be maybe the most famous theorem in pure mathematics, Fermat's last theorem. So if you weren't aware, this was originally suggested by Pierre de Fermat, that there are no solutions to a to the n plus b to the n equals c to the n in whole numbers whenever n is bigger than 2, so we're not in the Pythagoras' theorem case, apart from the obvious ones where one of the numbers is equal to 0, and so you can have b equals c and a equals 0. So this was conjectured a very long time ago by Pierre de Fermat and proven by Andrew Wiles, and of course you're in the Andrew Wiles building, so I felt obliged to use this as an example. And OK, so this is a problem to do with whole numbers. You just take a number a, you multiply it by itself, n times, you add it to a number b, which is multiplied to itself n times, and does this equal c for some number c multiplied to itself n times. And this involves whole numbers, and it involves multiplication. So you might naturally think that you can start to analyze this by thinking about prime numbers. And it's a result that rather than having to worry about all possible whole numbers n, you can just concentrate on when n is a prime number. So you're only multiplying your numbers together a prime number of times. And this is actually, it might seem that this doesn't make the problem much easier, but there's lots of special properties when n is prime, which does actually make this problem technically quite a lot easier. So let me roughly sketch the idea of this claim. So imagine, let's think about the case when n is 15. So we're thinking about a multiplied to itself 15 times plus b multiplied 15 times. Does that ever equal c multiplied 15 times? And imagine that Fermat was wrong. This is the sort of fake news thinking that mathematicians like to do all the time. We like to imagine all these crazy worlds where true things are false and false things are true. So imagine there was some example of some numbers a, b, and c such that a to the 15 plus b to the 15 equals c to the 15. Well, a to the 15 is a multiplied together 15 times, but rather than doing that, I could take a, multiply it together 5 times, and then multiply that number to itself 3 times. So in mathematical language, that's saying a to the 15 is a to the 5 to the power 3. It's just two different ways of collecting 15 lots of a together and multiplying them all together. But that means that if I did have numbers a, b, and c where a to the 15 plus b to the 15 was equal to c to the 15, I would have that a to the 5 to the 3 plus b to the 5 to the 3 would equal c to the 5 to the 3. And so this means that I would have a counterexample for Fermat's last theorem when n equals 3. Because I've now found 3 numbers where when I raise them to the third powers, I get a counterexample to Fermat's last theorem. So if I had a counterexample for 15, then I'll get a counterexample for 3. And very similarly, a to the 15 is a to the 3 to the 5, so I'd also get a counterexample for 5. And if you think about it a little bit, this example works in general, that if I have a counterexample for any integer n, then I get a counterexample for any prime factor of n. And so it's essentially enough to prove Fermat's last theorem when n is prime. I've skipped over the case when n has just got lots of prime factors which are all equal to 2, but this was a case that was already known to Pierre de Fermat, so we can just assume that. And the point of this is, again, we've taken a problem involving whole numbers and multiplication, and we've reduced it down to a problem involving prime numbers. So Wiles's result is famous, and it's really a pinnacle of modern mathematics. It's exceptionally complicated. So unfortunately, there's not enough space on this slide for me to give the full proof. But before Wiles's work, there was nonetheless lots of other important partial progress to Fermat's last theorem. One reason that Fermat's last theorem became such a celebrated problem in mathematics is because it led to the development of so many different beautiful ideas in mathematics. And so one very old result, but maybe one of the first sort of fundamental results trying to attack Fermat's last theorem in general, was work of Sophie Germain back in the 1820s. So she was thinking about Fermat's last theorem, and she knew that she only needed to consider the problem when n was a prime number. And she realized that if p was a prime number such that 2p plus 1 was also a prime number, then there was a good way of attacking Fermat's last theorem. So if p was a prime such that 2p plus 1 was prime, then essentially there's no solutions to Fermat's last theorem with the exponent p. Now there's a technical condition about abc not being a multiple of p, which is like abc not being equal to 0, but this allowed to show lots and lots of cases of Fermat's last theorem which weren't known at all back in the 1820s. So this was really very clever ideas. Apart from, there's one natural question that arises. When does the assumptions of Sophie Germain's theorem actually occur? How many primes are there such that 2p plus 1 is also a prime number? Does this even ever occur? Okay, so it works for 3, because 2p plus 1 when p is 3 is 7, and so we get a few examples concretely. But now, if we think a bit, I've given you 2 examples of questions which boil down to a problem about prime numbers, and just like the other example, we don't know how to solve this. It's a famous problem that's been open for 100 years, and we don't know how to solve this, like the other example, because they're the same problem. That before I was asking, is p minus 1 over 2 a prime number? But if p minus 1 over 2 was a prime number, if you call that prime number q, then 2q plus 1 is a prime number. So these are just exactly the same question, rewritten slightly. And so here's 2 examples of problems that occur in the complete opposite ends of the spectrum. One is buying something on Amazon. One is trying to solve some cases of the most famous problem in pure mathematics. Both of them involve, maybe not obviously, but involve integers multiplied together. Because they involve integers multiplied together, you can start to study the problems using prime numbers, and you can certainly start making some progress if you knew that there were certain primes with certain properties. And these questions arise very naturally. And it turns out that for these 2 cases, exactly the same problem arises. Are there infinitely many primes such that 2p plus 1 is a prime? And this is a problem that, despite having been studied for several hundred years, mathematicians still really don't have any clue of how to prove it. We all believe it is the case, but we have no idea of how to prove it, really. Okay, so finally, for the time I have left in this talk, I'd like to talk a little bit about some positive results. So as I mentioned, maybe at this stage in the talk, you're moderately convinced that at least with my examples, there's some problems involving whole numbers. They can be broken down into simpler problems involving primes, but you might feel that every time I have a problem involving whole numbers and break it down into a problem involving primes, I run straight into a brick wall because I get into some problem involving prime numbers, which all these super smart guys from antiquity have thought about and failed to solve. And so how on earth are we possibly going to make any progress? So, and these are really the sorts of problems that I like to think about day to day. I do not work on encryption. There's maybe people in this audience who are much, much more expert on this than me. Similarly, I don't work on trying to solve explicit equations like Fermat's last theorem, although I do like things like that. What I really like to think about is how many just very basic properties of the primes. How many primes are there with a certain property? So we've seen a couple of examples today. The question arose, how many primes are there such that p minus 1 only has small prime factors? Another question was, how many primes are there such that p minus 1 over 2 is prime? So I guess I mentioned the Riemann hypothesis. How many primes are there which are less than some large number x? So this is a case of something where we did make some partial progress. So we know the prime number theorem that says approximately how many numbers there are. The Riemann hypothesis is really about what does approximate mean and how accurately can we describe this number. And then one other question that's, again, a big famous open problem, but is particularly close to my heart, is how close can primes be to each other? Are there infinitely many pairs of primes which differ by exactly 2? So I mentioned right at the beginning of the talk that we can understand gaps between integers very easily because integers are just generated by 1, so somehow all gaps on the number line are of size 1. And I also mentioned that all primes bigger than 2 are even, so apart from the primes 2 and 3, all gaps between primes have to be of size at least 2. And then one very natural question on the basic distribution of the primes, almost one of the easiest questions you can possibly ask is, do these gaps occur often, or is it the case that the gaps gradually get bigger? If you think about the square numbers, for example, the gaps between square numbers always get bigger and bigger and bigger. as you look at bigger and bigger numbers. And we know that typically for prime numbers, the gaps get bigger, but actually we believe there should be infinitely often these rare primes that come clumped very close together. So these are about as simple as questions you can possibly ask if you're just interested in basic distributional questions about the prime numbers. And so these are the sorts of questions that I like to think about. I would be exceptionally happy if I could really answer any of these questions in a very strong way. But my aim is to develop flexible tools to try and understand something to do with the distribution of the primes, and to give some hints that there has been progress made on these problems. For the question of gap stream primes, we now know that there's some even number h less than 246. 246 is just a slightly artificial number that comes out from some computations, that there are infinitely many pairs of primes that differ by exactly h. So if rather than saying some number h less than 246, I could take h equals 2, I would have proved the twin prime conjecture, and I'd be very happy indeed. Unfortunately, we don't know how to prove the twin prime conjecture, but up until 6 years ago, we didn't know at all that it couldn't be the case that the gap stream of the primes got bigger and bigger and bigger, in the same way that the gap stream of the squares gradually get bigger as you look at bigger and bigger numbers. But we now know at least that they do clump together infinitely often, even if we don't know precisely how it happens. Similarly, I mentioned several times the two examples in my talk boil down to a question about, are there infinitely many primes such that p minus 1 divided by 2 is a prime number? And again, unfortunately, I don't know how to solve this. I would love to be able to solve that. But in the same spirit as the first theorem, it is the case that relatively recently, we do know that there are two fixed numbers, a1 and a2, such that there's infinitely many primes p with p minus a1 divided by a2, also a prime number. So if I could take a1 to be 1 and a2 to be 2, I would have solved the original problem. I can't quite do that. I need a little bit more flexibility. But this is exciting progress that we've made on some of these famous 100-year-old problems. So I'm nearing the end of my time now, so I just want to recap some of the things that I've hopefully talked about today, and I hope you found interesting. So there's lots of interesting and important questions that arise both in the real world and in pure mathematics that involve whole numbers. And whole numbers are somehow some of the most basic fundamental objects that you can possibly imagine in the universe. But whenever these problems involve multiplication, which is empirically quite often, then often these problems can be broken down into simpler problems involving prime numbers. And so if you understand the primes very well, then you could solve your original problem and you'd be really happy. Now, so therefore, people like me try and understand the distribution of the primes in general as a flexible toolbox so it could work for any problem that someone else comes. Mathematicians tend to get quite specialized as they get older. So I work on prime numbers, but I have lots of colleagues who work on other things. So the sorts of interactions are often someone will come to my office and say, hey, I could do this really great thing in my field if only I could understand this other problem to do with prime numbers. Do you know if this is solvable or not? And if we're very lucky, I'll say, yes, I know how to solve that. We can write a paper together. More often I say, unfortunately, this is a famous 100-year-old problem, so we can't do anything. But such is life. So unfortunately, often you can break it down and you can see a path to solving the original problem, but you run into these big hard walls of these famous fundamental problems about the distribution of primes, because realistically, we hardly know anything about the distribution of primes. Slightly embarrassing for me to say. But very slowly, we are making progress, and we are gradually understanding the primes, slowly but surely. And so it's actually a very exciting time in the field, and we feel that it's current and progress is being made, and we are able to understand these problems much, much better. So I think I'm going to stop there. Thanks a lot for listening. I hope you enjoyed the talk.